Hello tutoring, and this is our first video covering the first part of the first topic of the GCSE course, which is energy. And in this little bit we are covering energy stores and work done. So as you can see, this is the first of 3 videos covering the energy topic, so let's get right into it. So energy is just a concept. The concept of energy emerged in the 19th century. The idea was used to explain the work output of steam engines and then generalised to understand other heat engines, and it also became a key tool for understanding chemical reactions in biological systems. So you don't actually know any of this. This is just a little bit of motivation to get you into why the study of energy is important, especially in a world where fossil fuels and global warming is such a problem. So limits to the use of fossil fuels and global warming are critical problems for the century. Physicists and engineers are working hard to identify ways to reduce our energy usage. The key bit of information that I would like you to get from this slide is what energy transfer is. Work done is just energy transfer. So in this topic and in future topics when we'll refer to work done, it just means energy transfer, because energy is the ability for a system to do work. So, for example, if I put energy into a kettle, I am heating the water up. I'm changing that system. I'm giving the water a higher temperature. If I move an object with a force, I am doing work on that object because I am moving it. I'm moving it into a different position. You know, it's the ability to do work, to change a system. That's really what energy is. So we call different types of energy stores. So for example, something hot will have energy in its thermal store. And I want to see if you can come up with some different types of energy stores before I tell you. So if you're following along with your workbook, do task 1. Okay, so the types of energy store. We'll have magnetic, and magnetic energy is energy in magnets and electromagnets. We have kinetic energy, and that's the energy in moving objects, like a train. We have thermal energy. That's the energy in objects because of their heat. So, like this hob, you've got heat in the hob. You have light energy, and that's energy associated with the radiation, and it's what allows us to see. So, coming from torches, coming from lights, electromagnetic radiation, which we'll cover in a later video. All this is light energy. You've got gravitational potential energy, and that's the energy stored in raised objects. And you also have chemical energy, and that's stored in food and fuel and in batteries, and that's really the energy which is responsible for chemical reactions, and you find it in bonds, in particles and that sort of thing. That's chemical energy. There's sound energy, and that's energy released by vibrating objects like a guitar or a drum or something like that. And then there's electrical energy, and electrical energy is energy stored when a charge moves or held by static charges. So, energy flows through your wires when you use an electrical appliance. There is elastic potential energy, and that's stored in stretched or squashed objects like a spring. If you compress a spring, you're given the spring potential energy. When you let go, it's going to extend and move the spring back to its original position. And then you also have nuclear energy, and nuclear energy is stored in the nuclei of atoms. So in the middle of atoms you have neutrons and you have protons, and there's a lot of energy which is stored in keeping those together and in the middle of atoms. That's quite complicated, but again, we'll come to that in a later video. Nuclear energy. So systems are an object or a group of objects. When we talk about energy, we often talk about the idea of systems. When a system is changed, there are changes in the way energy is stored. So you can think of a system as, I don't know, let's say we have a fire. If we change the fuel of the fire and we heat the fuel up, eventually it might turn into a fire, and we're changing that system, aren't we? We're changing the fuel by heating it up. And what you'll get is you'll get a change of energy from the chemical store in that fuel to the thermal store when it makes a fire, and then the fire will release light as well, so you'll have light energy, and it might even crack a little bit, so you might have sound energy as well from the fire. So when you change a system, you change the way energy is stored. One of the biggest ideas in this topic is the conservation of energy. You've probably heard this before. It's quite a famous sort of phrase that energy can't be created and it can't be destroyed. Energy can be transferred from one type to another when a system changes, but you cannot create energy and you cannot destroy energy. You can only transfer energy between stores, different types of energy. So how can a system be changed? Well, a system can be changed and therefore energy can be transferred by heating. So you can heat things up, that's a way of transferring energy. You can change a system and transfer energy through work done by forces. So a force acting on a system, that's work done, that's a change in energy. Work done when a current flows as well. So if you have a wire and a current flows through the wire, you are essentially, work is being done when that current flows. You are changing the types of energy stored when the current flows into electrical energy. So when an object is raised, so brought upwards, energy changes from kinetic energy into gravitational potential energy, which is quite often shortened to GBE. So if we take an object like this pen and we raise it upwards, the kinetic energy which I've just given that pen to make it travel, we call travelling, the energy given to moving objects is kinetic energy. So if we make this pen travel upwards like that, the kinetic energy is being transferred into gravitational potential energy, because when I drop it, it moves back down again. The energy which is used to push up the object is converted into gravitational potential energy, as we've just seen by that pen. So a moving object colliding with an obstacle, if you have something which collides into something else, energy is transferred from the kinetic energy store to the sound and heat energy store. So if you have a collision between two cars, for example, you will hear a big bang, because the kinetic energy of those two cars, it has to go somewhere, it has to change into another type of energy because it can't be created or destroyed, so it needs to go somewhere. It goes into the sound store because you hear the collision, or it might go into the heat store where you have friction between the cars. When two cars collide with each other, there might be friction and you might get a lot of heat produced there when the cars collide as well. This is because the energy which is used to push the object is converted into heat due to friction and sound due to vibrations of the objects, as we've just talked about. Resultant forces mean that objects are accelerated. When objects are accelerated, chemical energy or magnetic energy or whatever is causing these objects to accelerate, that's transferred into kinetic energy. So when you have a force acting on an object and the object starts to move, you're doing work on that object and you are giving it kinetic energy. The magnetic energy in the magnet is being converted into kinetic energy as the object moves. In muscles, chemical energy is changed into kinetic energy too. So if you're thinking about your muscles in, let's say, your arm, and you pick something up, the energy which is causing that kinetic energy to make your arm move and to pick the object up, that needs to come from somewhere, and it comes from the chemical energy in your muscles. That's how muscles work. They convert chemical energy into kinetic energy. When a vehicle slows down, kinetic energy is transferred into heat, and in some cases sound energy. This is because brake pads, they cause friction, slowing the wheels down, but also building up energy in the thermal store. Kinetic energy is converted into heat energy. So if you're on a bike, for example, and you pull your brakes, you will get these little brake blocks which compress onto your wheel, and when they push onto the wheel, they cause friction between the wheel and the brake pads. And what you'll find that the kinetic energy in the bike transfers into heat energy in the brake pads. And because the kinetic energy is coming down, your speed will lower, and essentially that's how brakes work. They slow the vehicle down by transferring that kinetic energy into heat energy. In an electric kettle, electrical energy is transferred into heat energy. This is because the electrical energy enters a wire of high resistance, which causes electrical energy to be converted into heat energy, meaning the heating element has energy in its thermal store. So electrical energy is converted into heat energy or thermal energy in kettles, and that's how you boil your water. Okay, if you're following along in our workbook, you can now complete task 2, please. Okay, so this now is the introduction to the quantitative side of energy. Quantitative is to do with numbers. There's a lot of formulas in physics in general, and we're starting to look at some of those formulas now. Unfortunately, you're not given a lot of the formulas in the exam, so you do need to remember them. But after some practice, it becomes a lot easier than what it might feel at first. So there's certain ways that energy can be transferred where work is done, so where you're changing energy store, which have formulas that you need to know. There are 3 formulas which you need to learn for energy transfer. Remember work done? Work done's another name for energy transfer. We've been through this quite a few times already. Mechanical work involves using the force to move an object, and electrical work involves current transferring energy. So work done is just another name for energy transfer. Mechanical work, or work done by mechanics if you like, involves using the force to move an object, and electrical work is electric currents transferring the energy. So you can work out energy after a force acts upon an object if you know the force applied to an object and the distance travelled. So you need to know the force applied and the distance travelled. You can work out the work done. You can work out the energy transferred. And the first formula of the course is that work done is equal to force times distance. So the first equation that you must know for energy is W equals Fd. Work done, or energy transfer, is equal to force times distance. Work done is energy, so that's measured in joules. Force is a force, so that's measured in newtons. And distance is measured in meters. Okay, so if you're given different units in the question, you need to convert into joules, newtons, and meters. So, worked example. Work out the work done by a dog pulling a sled with 70 newtons over a distance of 5 meters. Well, we can write down our formula. Work done is force times distance, or W equals Fd. The work done is equal to 5, because that's 5 meters, multiplied by 70, because we have 70 newtons. So our work done is 350. Work done is measured in joules, so my final answer is 350 joules. Another worked example. During an earthquake, tectonic plates move. An earthquake of magnitude 6 uses 7 million kilojoules of energy and moves a distance of 1.5 meters. So the tectonic plate moves a distance of 1.5 meters. Calculate the force exerted on the plate. Okay, so we'll write out our formula again. Work done is force times distance. This time, our unknown value is on the right-hand side. So we've got 7... Is that 7 million? No, it's not. Sorry, it's. We seem to have went from 7. Oh no, sorry, that's maybe in depth. We'll have 7. Say this is how important it is to look at your units. We'll have 7 million kilojoules of energy. It almost tripped me up there. So kilojoules of energy. Kilo is 1,000. So 7 million kilojoules. Well, that's 7 million thousand joules of energy. So transfer 7 million kilojoules into joules, will have 7 million thousand joules, or 7 with 9 zeros. So we have 7 billion joules divided by 1.5 to get our force. Because we rearrange that formula, we need to divide both sides here, both sides by 1.5 to get our force by itself. Our force then, if we evaluate that, gets 4,666,666,666.66 newtons of force. And we can convert that back into kilonewtons, if you like, because that's a lot of numbers to write down. So we can shorten that to 4,666,667 kilonewtons. And in your exam, you wouldn't need to give it to that many significant figures. Okay, so you can work out energy after a current flows. In electricity, we will cover energy, charge, and voltage later on down the line. But the formula comes up in the topic of energy too. So do you know the formula already? I'm guessing you probably don't. The formula is work done is charge multiplied by voltage. Again, you need to learn this. It's not given to you in the exam. Work done is charge times voltage. W equals QV. And that's the second equation which you need to learn. So another worked example. James charges his phone with a 12-volt supply. In an hour's worth of use, he uses 500 kilojoules of energy. What is the amount of charge that his phone must have? What is the amount of charge which is transferred into his phone? Well, again, we're going to write down our formula. Work done is charge times voltage, W equals QV. 500,000 is equal to Q multiplied by 12. So again, we're going to rearrange this formula by dividing both sides by 12. So we'll get rid of the 12 on this side and we'll divide by 12 on this side. So our charge is equal to 41,666.66 coulombs. Charge is measured in coulombs. Just going back to that really quickly. Work done is, again, that's an energy, so that's measured in joules. Charge is measured in coulombs and voltage is measured in volts. So our final answer is 41,666.66 coulombs. Again, in the exam, you wouldn't need to write it quite to that amount of significant figures. Right, so you should now complete task 3 if you're following along in your workbook. Okay, so you can work out energy after an object has moved. If you know the mass and the velocity of the object, you can find out how much work has been done when the object has moved. Our next equation which you need to learn is work done is equal to half the mass multiplied by the velocity squared. W equals half mv squared. Work done, again, that's measured in joules because it's an energy. Mass is measured in kilograms and velocity is measured in meters per second. Okay, so work example. A killer whale of mass 2,000 kilograms moves a distance in the sea. If the whale was travelling at a velocity of 5 meters per second, what was the work done by the killer whale? Well, write out our equation first of all. W equals half mv squared. Work done is half the mass times the velocity squared. Put in our numbers. So work done is half multiplied by 2,000 multiplied by 5 squared. W is, well, half of 2,000 is 1,000 and 5 squared is 25. Our final value for work done, if you evaluate that equation, is 25,000. So the work done, or energy, is measured in joules. So my final answer is 25,000 joules, or, if you're clever, you can write it as 25 kilojoules, 25,000 joules. Okay, if there wasn't enough equations and numbers already, there is, unfortunately, just a couple more equations that you need to learn for the first little bit of energy. And yeah, we'll crack on, we'll get through it, don't worry. You can work out energy after a spring has been extended or compressed. So if you take a spring, you can extend it and you feel a force, you get energy put into its elastic potential energy store. And if you know the spring constant of the spring and the extension, the new length, minus the original length, then you can find out how much work has been done in stretching / compressing the spring. Our next equation that you need to learn is that work done is half the spring constant multiplied by the extension squared. W is half KE squared. And again, you need to learn this. This is one of the ones that you need to know. And here is a worked example using that equation. So an ordinary spring is connected to a plank of wood. The original length of the spring is 0.3 meters. Once the spring is connected, it stretches out to 0.5 meters long. If the work done by the wood on the spring was 100 joules, calculate the spring constant of the spring. So that's quite a wordy question, so we're going to sort of decompose that a little bit, okay? So it wants you to work out the spring constant of the spring. So if we write out our equation, we've got that W is equal to half KE squared. The spring constant is the K, so we've actually got quite a complicated formula here because we've got 100 on one side and we've got all of these different things on the other side. The original length of the spring is 0.3 meters and the final length of the spring is 0.5 meters. So we want the difference to find the extension. So we're going to plug those numbers in here to find the difference, which comes to 0.2, okay? If we evaluate that, 0.2 squared, we'll get 0.04. What we need to do is we need to divide both sides by this 0.04. and that'll be one step closer to having K by itself. So if we do that, we get that 2,500 is equal to half the constant, okay? So if we multiply both sides by 2, we'll get rid of the half on this side, and we'll get that the spring constant is 5,000. Spring constant is measured in newtons per metre, so the final answer is 5,000 newtons per metre. And I believe, finally, I believe this is the last equation that we need to learn for the first part. You can work out the gravitational potential energy of an object above the ground. If you know the mass and height of the object and the gravitational field strength of the planet which it is on, a lot of the time it'll be Earth, but you never know, you could be asked to work out the gravitational potential energy of something on another planet. You can work out how much elastic potential energy the object has. Gravitational potential energy is equal to the mass multiplied by the gravitational field strength multiplied by the height. So work done is equal to mass times gravity times the height. W equals mgh. Indiana Jones designs a trap to kill intruders. He suspends an anvil of 300 kilograms above a doorway. It is 9.81 newtons per kilogram gravitational field strength on Earth. If the anvil does 9,500 joules of work on an intruder, how high is the anvil? Well, write out our equation, W equals mgh. We have that 9,500 is equal to 300 multiplied by 9.81 multiplied by h. So, rearrange that formula. We want to get h by itself, so we're going to bring 300 and the 9.81 onto the left-hand side of the equation. So 9,500 divided by 300 multiplied by 9.81 is equal to h. If we evaluate the 300 times 9.81, we'll get 2,943. 9,500 divided by 2,943 gives h. So h, our height, is 3.22. And since height is a distance, it's measured in meters. So my final answer is 3.22 meters. Complete task 4 in your energy workbook if you're following along. Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backrowtutoring.com.